Today I'm going to be explaining something that has appeared in the nightmares of many high school students, the child of Isaac Newton and Gottfried Leibniz, aka calculus. But calculus doesn't have to be this scary, intimidating monster because it's a simple idea that deals with instantaneous rates of change. Let's say that we wish to measure the change in a variable y with respect to a change in a variable x. Now, supposing we draw a curve to demonstrate this relationship between y and x, we can see that the steepness of the curve is increasing. Initially, a small change in x leads to a small change in y, but as we move along the x-axis, a small change in x leads to a much larger change in y. It seems as though there is no easy way to calculate the instantaneous rate of change in this case, as the rate of change is not constant. In contrast, it is much easier to calculate the instantaneous rate of change in a straight line, because the rate of change is constant throughout. Let us consider the function 2x. We could take any pair of coordinates on the line and we would calculate the same change in y for a given change in x, because the slope or the gradient of a straight line is constant. A straight line does not change in steepness. In this case, we can see that the rate of change is 2. That means that every time x changes by 1 unit, y changes by 2 units. So we have seen so far that we wish to calculate instantaneous rates of change, but it is much easier to do so for straight lines as opposed to curves, because straight lines have a constant rate of change. But what if we could apply the same logic that we use to obtain the rate of change of a straight line for any function, whether it's a curve or a straight line? And as it turns out, this is exactly what calculus does. I'm going to explain this by using a simple analogy. Let us consider a round object that we are familiar with, our Earth. The Earth, as we can see from my drawing, is shaped like a potato. So our Earth is round, but somewhere on this great planet of ours, I could zoom in and see you standing on a street. The street is a straight line and definitely does not appear curved to you. The Earth contains many such flat streets even though it's a round object, and this leads to an interesting question. What if all curves are made up of a very large number of extremely minuscule straight lines? Let's use this insight to formulate a general rule to calculate the rate of change for any function. Let's consider a function whose graph is a curve, and let's zoom in a lot on one particular point. Given that we zoom in enough, we will see a straight line that makes up that part of the curve. Now all we have to do is pick a pair of coordinates. So let the first pair be x, f of x, and the second will have to be a value that is a very small distance away from x. So let's call that x plus h, f of x plus h. H is a very small value, so small that we can say that h tends to 0, meaning that h isn't 0 but it is smaller than all positive real numbers. Now let's divide the change in y by the change in x, as we would do for any straight line. The change in y will be f of x plus h minus f of x, and the change in x will be x plus h minus x, where x and x will cancel out. This gives us f of x plus h minus f of x divided by h, where h tends to 0. So we can see that we have come up with a simple rule using very basic ideas of rates of change that allows us to measure the instantaneous rate of change of any function. This is what calculus is. And I think we can safely say that calculus is no longer the scary monster that it seemed to be.